Hello, my name's Dr. Matt Padula, and I'm here to talk to you at length in 6 different videos about mass spectrometry and how it relates to the analysis of biomolecules. Before I start, I just want to say that one of my main jobs other than lecturing is running the Proteomics, Lipidomics and Metabolomics core facility. Within this facility, we have numerous mass spectrometers. The ones that we use the majority of the time for biomolecular analysis are these two instruments, our aging Q-Exactive Plus system, the geometry of which can be seen in this diagram here, and we will come back to that in throughout the course of these lectures. And our newest instrument, our Waters Synapt system, the architecture which is shown here. And the main differences between these two instruments is the presence of this ion mobility separator, which we will come back to in, I believe, part 4 of our lecture series. Before I start getting into the instrumentation, what I really want to get across is the fact that mass is actually important. And the reason for this is that the elements and their isotopes all have unique masses. So as you can see in this table, you can see the atomic weight of some of the elements, and I'll draw you a special attention to the isotopes of carbon, where carbon is the most abundant isotope of carbon, carbon-12, is set to be exactly 12, and everything is measured relative to the mass of carbon. So carbon has 3 isotopes, carbon-12, carbon-13, and carbon-14, which is radioactive and does decay. Carbon-12 and carbon-13 will become important as we go on. And so the reason for this is that carbon has 6 protons, no matter what isotope it is, but the number of neutrons in the nuclei changes, which means that the mass of a carbon atom that is C13 is essentially 1 Dalton heavier than its relative C12. This will become important as we go on because it allows us to look at different charge states of isotopes to be able to work out the mass of things measured by the mass spectrometer. But what we want to get to here is that by knowing the exact mass of the elements and by knowing chemical formula, we can calculate the mass of ions and things that we want to measure. Now, what a mass spectrometer does is it measures the masses of elements and it measures the masses of compounds, but not unlike your kitchen balance. But what it does is it does this really, really fast, typically 20 milliseconds per scan, sometimes even faster. So we can use mass spectrometry to measure the mass of various molecules. So as I said, we can calculate the mass of a compound from its constituent elements. So here, with one of the favorite compounds of students, ethanol, we have this chemical formula and we can use it to calculate this mass. And the mass spectrometer can be used to verify and measure that exact mass. Same with something like sucrose. From the chemical formula, we can calculate its exact mass. For other compounds like solanine, which is the green thing that's found in potatoes, lipids, where we can calculate their exact mass, and especially peptides, where we can get their elemental composition. We know the masses of individual amino acids. This is the amino acid sequence. We can calculate the exact mass of the peptide. But knowing the exact mass of the peptide does not necessarily allow you to differentiate between isotopes of different compounds or structural variants of different compounds. So this is a very simple example where we've got the mass spectrum of 2 forms of pentanone. Each of these has exactly the same chemical formula, illustrated here. They have exactly the same intact mass, but they have quite different structures. And the way that we can differentiate between these two structures is we can take the intact molecule and we can smash it with the mass spectrometer and we can measure the masses of the fragments. So what you can see here is that for this structure, we get this unique fragment at 71, we get this unique fragment at 43. For this structure, we get this unique fragment at 57 and this unique fragment at 29. And so therefore, we can tell the difference between these two compounds based on their fragmentation spectra. So how does a mass spectrometer work? So we are not measuring the compounds directly as you would hold them in your hand as a dry powder. What we have to do is we have to turn those compounds into ions. We have to make them charged molecules that we can measure in the gas phase. The way that we do this is we need an ion source where we can either put the compound into a volatile gas state, which is often used in gas chromatography, which we're not really going to talk about, or we can use techniques like electrospray and MALDI that we're going to talk a great deal about. Once we have generated those ions, we need a way of measuring them, and these are typically by time of flight, quadrupoles, ion traps, or hybrids of these things, which we're going to talk about in detail in future videos. And then we needed a way of detecting and measuring the abundance of those ions, and there's a number of different ways of doing that. So there's loads and loads of different types of mass spectrometers. There's numerous companies that are out there. This particular slide is a few years old, but you can see the diversity of different instruments in various vendors' ranges. If we update it for now, these are some of the typical types of instruments that we see in most labs. Thermo instruments, like based on the Orbitrap platform, Bruker instruments based on their ion mobility time of flight platform, SciEx with their time of flight platforms, Waters with their ion mobility time of flight platforms, and another Thermo instrument here that we'll talk about as we go on. I want to spend a little bit of time talking about the history of mass spectrometry because it has been around for a really long time. So the first mass spectrometer was built by a guy by the name of J.J. Thomson, and he's a very famous physicist, came up with a lot of very key insights in physics. But what he did was he ionized neon through a magnetic and electric field and was able to show that you could deflect these ions onto a photographic plate to measure them. So you can see things like, especially these two down here, where you've got this single pulse here, which is carbon monoxide, but then you've got this wider pulse here, and JJ realized that this was because neon has two isotopes, one that's 20 and one that's 22. This gentleman, Aston, who was a colleague and a student of J.J. Thomson's, he then refined mass spectrometry and used it to identify and validate the presence of 212 out of the 287 suspected isotopes. And this was used to come up with this whole number rule that was then used in nuclear research. Another student of JJ's came up with an instrument that was 100 times more accurate, and this was used to discover the uranium-235 isotope. And then probably most famously, Bainbridge used mass spectrometry to verify Einstein's equation, energy equals mass times the speed of light squared. And he did this by precisely measuring the mass differences between these nuclear isotopes. If you want more information about this, there is a Wikipedia page about Bainbridge. His other claim to fame was that he was one of the directors of the Trinity test for the Manhattan Project. Now, one of the early uses of mass spectrometry was also for the enrichment of uranium that was used in the bomb that was dropped on Nagasaki. So this device here is a series of things called calutrons. So each one of these devices in here is actually a mass spectrometer, and it's a magnetic sector device. And what you would do is you would load your raw uranium into it, and it would go round and round and round in a circle within the instrument and the 238 isotopes would get deflected away and collected onto a metal plate. That metal plate would be taken out, the uranium scraped off, and it would be put back in. And this would continuously happen. So this is a device called the Calutron. And so one of the things that I ask students is, if you're going to operate mass spectrometry, do you want to be associated with the technology that caused one of the single largest the single largest losses of human life ever? Because mass spectrometry was integral into creating this atomic bomb. One of the poor jokes that I also make is that this is the aftermath of Nagasaki in 1945, and this is the aftermath of a tsunami. I'd like to know what this monument is actually made out of. Now, the joke has actually changed. It is actually a poor joke because this is not Nagasaki, but the story remains. These shrines are pretty tough. So first we have to define some terms before we go on. So we're going to define each of these terms in progress. Before I do, one of the things that I need to make clear is that when I'm talking about a protein or a sugar or a peptide or a biomolecule, I'm not talking about one molecule. I'm talking about hundreds to thousands, tens of thousands of exactly the same thing, the exact same elemental composition, because mass spectrometry is a concentration sensitive technique. You need a number of molecules to detect things. So for many biomolecules, we don't have the equivalent of a PCR like we do with DNA and RNA. So we can't amplify the number of molecules. If we want more sensitivity, we need to load more. But there are caveats and problems with that, and I'll come back to those in a later video. But what I want you to realize is that there's not one molecule of the thing that we're measuring, there's lots. And that actually has ramifications for the way that this works. So I now want to describe mass to charge ratio. So what the mass spectrometer actually measures is not mass, it is the mass divided by the number of charges. So here I remind you of the fact that carbon has multiple isotopes. We're going to concentrate on C12 and C13. C13 having one extra neutron in its nuclei. So this is the mass spectra for solanin, the structure of which is shown here. This peak here at 868.5 is the population of ions where every single carbon in here is C12. This population here is the molecules of this where one of the carbons is C13. And in different molecules, that carbon 13 can be in different places. In one molecule, it might be here. In another molecule, it might be here. In another molecule, it might be here, and so on. You can look at this. You know that this molecule has only one charge because the mass divided by the one charge ends up being the calculated mass. And the difference between these two is 1 Dalton, which is the mass of the neutron. Why this becomes important is when you start talking about multiply charged ions, like peptides. So in this case, a tryptic peptide, where you've got arginine on one end with this amine, and you've got the N-termini over here with this amine, those can both become positively charged under acidic conditions. So this then provides this mass spectrum where this is the population of molecules where every single carbon is C12. What you'll notice here is that the mass of this is 785.8. But if you actually calculate the mass of the peptide from its elemental composition, you get 1,570. You then need to add the mass of the two hydrogen ions, and you end up with 1,572. Now this is not 1,572, and the reason is because we're measuring the mass of the molecule divided by the number of charges. The quick way that we can use to determine that this is a multiply charged ion is the fact that the difference between the C12 and the population of C13, so this is the population of molecules where this carbon could be C13 in one molecule, this carbon could be C13 in a different molecule, so on and so forth. The difference between this and this is 0.5 of a Dalton, because if we take the mass of the peptide from its elemental composition, we add the mass of the neutron, and we add the mass of the two hydrogens, we end up with this. We then divide it by the number of charges, and we end up with this. So that neutron mass gets halved, and so the distance between here and here is 0.5 of a Dalton. If it was triply charged, the mass difference would be 0.33. If it was 4 charges, it would be 0.25, and so on and so forth. The next thing that I want to talk about is resolving power and resolution, which basically means how narrow can you make these mass peaks where you actually get baseline definition of these mass peaks. This becomes important, and the way that you calculate it is based up here. The larger this number becomes, the higher the resolution. So these two mass spectrums are both this molecule being measured. The reason that this starts to become important is for a couple of reasons. The first one is that you can actually start to determine the elemental composition of a compound just from its intact mass at a high enough resolution. So this is the compound that's being ionized, but if you didn't know what that compound was, you could start to suspect its elemental composition from looking at some of these isotopes down here, where at 500,000 resolution, this isotope indicates that there is a sulfur group in there, and this one is just the mass of the thing with 2 C13s in the molecule somewhere. But you can see this shoulder that's starting to occur over here. If you go from 500,000 to 1 million, this then resolves out into a peak by itself, and this indicates that there is an oxygen somewhere in this compound, and that is borne out by the structure where there is actually numerous oxygens in this molecule. Oops, oh sorry, the composition is actually this guy that's under here. The sulfur is in this position here. When you come to intact protein analysis, where you've got really, really large molecules, you can start to work out the mass of the molecule from the isotope series in a particular charge state. So what I'll come back to this in a little while, where electrospray creates multiply charged molecules. And so each one of these peaks is a different charge state for myoglobin, which has a mass of 1651. If I zoom in on this charge state, I can start to see these are the individual isotopes, where this is the collection where it has, you know, so many C13s, one extra C13, another extra C13, so on and so forth. And with this really high resolution of these in the charge state, you can start to calculate accurate masses from this composition. Mass spectrometers is not perfect. You need to understand what the mass error is and be able to measure it and be able to minimize it as much as you possibly can. This is the way that you determine the mass error, and it's normally expressed in parts per million. It's an interesting equation because as you go down in mass over charge ratio, this error gets larger just because of the way that the equation works. Sensitivity is just as simple as what is the minimum amount of a molecule that can be detected. And this is going to change from molecule to molecule because different molecules ionize with different efficiencies. And that's something that you need to be aware of. So that's all I'm going to talk about in this particular lecture. In the next lecture, I'm going to start to talk about the way that we ionize samples. Firstly, we're going to talk about MALDI, and we're going to talk about how MALDI is interfaced with time of flight. The lecture after that, we're going to talk about electrospray and how that's interfaced with time of flight, but also quadrupoles, cyclotrons, and orbitraps. And we're also going to talk about ways that we detect ions. So I will look forward to seeing you in the next lecture.